let's say we have f of x equal to cosine of x to the x cubed power. So we want to find the derivative of this. So personally, when I'm doing logarithmic differentiation, which I know I'm going to do when I have a variable in my base and my exponents, I'm going to let the thing be called y. Thank you, thank you. And I'm going to take the natural log of both sides. The whole reason for doing this is so we can bring that exponent down. So I'm going to rewrite this as the natural log of y equal to x cubed times the natural log of cosine. I should point out, because I don't think anyone's done it this the other way, but just in case, some people do like to do it this other way, but they say, I'm going to do y is e to the natural log of cosine of x to the x cubed power, and then rewrite that as y equal to e to the x cubed times the natural log of cosine of x. That is another way you could go if you wanted to. It's not the way I've been showing you guys how to do it. So if this doesn't look familiar to you, ignore it. Do it this way. Doing it this way, we then take the derivative of both sides. This is where you have to remember y is a function of x. So when we differentiate the natural log of some function of x, the natural log of some stuff, the derivative is going to be 1 over the stuff times the derivative of the stuff. On the right-hand side, we're almost always having to use some combination of usually the product rule, or sometimes the quotient rule will pop up, sometimes the chain rule, usually the chain rule. Here we have to use the product rule. This is some f times some g. My derivative is going to be f prime g plus f g prime. Let's see, my f prime is 3x squared. G is just the natural log of cosine of x. F is x cubed. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Typically, we simplify this a little bit if we can. I'm going to write this part here as x cubed times, or I'm really going to write negative x cubed times tangent of x. And then, but I'm also going to multiply both sides by y. So y prime is going to be y times 3x squared times natural log of cosine of x minus x cubed times tangent of x. And then finally, I'm going to replace y with what y is equal to. So the derivative of y prime is going to be cosine of x to the x cubed times all of that. 3x squared natural log of cosine of x minus x cubed times tangent of x. I will just mention, you could have done it this way if you wanted to. You could have said, oh, the derivative here, the derivative of e to the stuff is e to the stuff times the derivative of that stuff. And the derivative of that stuff is exactly the same as the derivative of this, right? Because it's, again, it's x cubed times natural log of cosine. So it's really just the e to the stuff times all of this again. 3x squared natural log of cosine of x minus x cubed tangent x. And your answer is the same because the x cubed natural log of cosine of x is just cosine of x to the x cubed power. Oops, you said, apologies. And this here is just the same as that. This really is the same derivative. Either way is fine, but you should definitely do it the way your teacher is showing you how to do it. So if I imagine most of you saw it this way, where you actually take the natural log of both sides. But I know some people in the past, and maybe this quarter have done it this way. So I just want to mention that. Questions about that? Thank you. Okay. Hopefully everything was good with Grant last week. I imagine it was. Grant's a great guy. Let's talk more about graphing. And there's one thing I wanted to start with graphing wise. I saw a lot of questions on one of the homework assignments that have like graphs of derivatives and graphs of other things and trying to identify various things. Let's just start with this. So, well, most of the time anyway, unless there's some weird questions where a horizontal line gives you a relative maximum, I can't help you with that because that's wrong to me. But here's what I would like you to see, know, think about, first of all. So if your function is increasing, the derivative is positive. And if your function is decreasing, your derivative is negative. So actually, I'm going to write this out. If f is increasing, that means f prime is greater than 0. If f is decreasing, that means the derivative is less than 0. And there are lots of pictures you can think of. I might think of maybe just like the absolute value. It's probably not a great example, actually, but that's okay. You can see over here, is the function increasing or decreasing? It's increasing over here on the right-hand side. Is the derivative positive or negative? In fact, it's always positive 1. So over here, right, the function, I should write it over here, sorry. F is definitely increasing. The derivative is definitely greater than 0. It's actually equal to 1. Over here, the function is certainly decreasing. The derivative is certainly negative. It's negative 1. Okay, well, I want to extend this idea a little further. And there's actually one specific set of pictures I really like to draw. And yeah, I could probably fit them here. I don't want to, though. Want to use another specific. So let's look at this for a second. Oh, sorry. So some things I want to write about this shape, they're all going to be this, they're all going to be equivalent. We're always talking left to right. As I move left to right, well, in fact, sorry, no, that's yeah. I actually really want to talk about the derivative first. I know, like, I usually start with the function. Let's start with the derivative. So we move left to right. My derivative, aka the slope of my tangent line, is increasing or decreasing? Well, over here, is the derivative really positive or really negative? Really negative, right? It's got a very negative slope. Over here, less negative. So the derivative increased. Over here, close to 0. Over here, a little bit positive. Over here, a little bit more positive. Even more positive. So for this shape, the first derivative is increasing. Okay, now here's how I want to look back. If something is increasing, its rate of change is positive. I'm going to say that again, but with different words. If something is increasing, its derivative is positive. So if something is increasing, its derivative is positive. And then, of course, this is concave up. Like a cup. Then we can say the same sort of thing if we flip it over. This function is definitely concave down. Like a frown. Here, the first derivative is decreasing. Starts off super duper positive, less positive, 0, negative, more negative. It's getting smaller and smaller throughout the thing. So the first derivative is decreasing. And the second derivative, well, the derivative of the derivative, right? If something is decreasing, its derivative is negative. So the second derivative is negative. So I want to emphasize, if you know something is changing in it, right? If something is increasing, its derivative is positive. And that's true for any function. So if you know the fifth derivative of a function was decreasing, you know the sixth derivative is negative. Always the derivative of whatever function you like is just the rate of change of the previous thing. Yeah, this should be, I believe this is being recorded. Now you've got me curious. Oh yeah, good. All right, yes, you said. They said, then they said like, oh yeah, I see. So that's kind of the main take. This is, I would encourage you to think about this, like when you have a question where, well, in fact, let's do an example. It's kind of like one of these funky homework questions. So let's say you've got something like, I don't know, try and make it not be super terrible. Yeah, let's see if I can. Let's say we got something like this. And this is a graph of the first derivative. This is the graph of f prime. And I want to identify a few things. What do I want to identify? First of all, I want to know where is the function itself increasing or decreasing. All right, well, this is the graph of f prime, and I'm going to label things as I go here because I'm just making this up. So this is the graph of f prime. I know it's going to be increasing if f prime is positive. So it's going to be increasing where f prime is greater than 0. So let's call this point A and this point B. It's going to be increasing everywhere from, oh, fine. I guess I didn't graph the whole thing. Sorry. We'll call this point here C, since I'm not going to graph more of it. So it's going to be increasing from C to A and from B onward, wherever the first derivative is positive. And it's going to be decreasing where the first derivative is negative. So between A and B. Okay. Can we talk about concavity? Maybe. So if someone asked me about concavity, well, I know it's concave down if the second derivative is negative. But this is the first derivative. Can we get there? Yeah. So we want the second derivative. So let's say concave down specifically. So we want the second derivative to be negative, which means the first derivative should be what? Right, the first derivative should be decreasing. Well, we can see that. We can see the first derivative is decreasing from here to there and from here to there. So I do a little more labeling. I'll call this E, F, G, and H. We can see that it's concave down from E to F and from G to H. What other kinds of things might we ask about this? It's not a rhetorical question. I'm really asking you guys, like, what else might you ask about this? What's that? Yeah, exactly. I mean, I say that's not exactly what I was thinking, but no, that's a very good answer. Exactly, extremas. So what about extrema? Where could we find relative maxima? Okay, well, you get a relative maximum when you go from increasing to decreasing. or when the first derivative goes from positive to negative. So it looks like we're going to have a relative maximum right there at A. We have a relative minimum at x equal to b. Right, because here the function is getting larger, right? So yeah, it's kind of, it can be a little mind like trippy. Like the function's getting bigger because the derivative is still positive. And then the function stops getting bigger and starts getting smaller because now the rate of change of the function, excuse me, is negative. And then it goes, right, the function is getting smaller, smaller, the function's still getting smaller because the derivative is negative. And then boom, right at b, the function itself starts getting bigger because the derivative is now positive. So, right, this is the graph of the derivative, not the graph of the function itself. So we have to think about everything that's going on here in terms of rate of change of the original function. This is telling me all throughout here, the function is growing because the rate of change is positive. It might grow really, really fast here, or it might grow not quite so fast over here. But everywhere from C to A, the function is increasing. Everywhere from B onward, the function is decreasing, or sorry, increasing. It's only between A and B where it takes a bit of a break and it decreases for a little. I guess the last thing we might ask about would be, where might there be an inflection point? Well, we can actually already answer that question because we answered the concavity question. If you know where it's concave up and concave down, the places where it changes concavity is where you have an inflection point. So it looks like we're changing concavity from, when we go from, let's see, from like here to there. Sorry, that's not, I should say that should be a point, not an interval. It looks like we're changing concavity at the point F. Because here, well, in fact, I'm going back here, right? The first derivative is decreasing here, which means it's concave down. The first derivative is increasing here, which means it's concave up. So we have to have an inflection point at F. And then first derivative is increasing, first derivative is decreasing, looks like G as well. Decreasing, increasing, looks like H as well. And probably also E, because we went from increasing first derivative to decreasing first derivative. So just like relative extrema are literally the maxes and mins of the function, inflection points are the relative extrema of the first derivative. Right here, the first derivative is equal to 0. No, that's not true. I'm saying the wrong thing, but it's not that bad. Here, the what's equal to 0. The second derivative, right? The derivative of this thing I've graphed, which is the first derivative. So right here, the derivative of the first derivative is equal to 0. And the same is true here and here and here.
So I'm kind of confused about the second derivative test. So when you
We haven't talked about that yet, but okay.
Okay. Like, what's the point of taking it?
I don't love it. I don't think it's a good test. We'll talk about it though. Okay. Other questions about this example before we move on to some graphs? Yeah. How do I find asymptotes for the original function? I don't think this graph has any. Yeah, in fact, I'm sure it doesn't have any because I drew it very smoothly. So let's actually, here's what I would say. Let's draw something with an asymptote. Let me get my notes in order here so I don't get them out of order. Sorry, everything's okay. So let's say we had a function. I'm assuming, would you mean a vertical asymptote or horizontal asymptote? Okay. So if you have something with a vertical asymptote, say it did this. Here's my function. We can draw the graph of that. So way over here, I should say we can draw the graph of the derivative. Derivative is positive or negative over here. definitely negative, 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 and right about here, maybe it bottoms out and gets to be 0. And then it's going to get very positive, like infinitely large positive, because the tangent lines get steeper and steeper and steeper and more vertical. So I would say my derivative is probably some sort of negative. And then it gets to be very, very, very positive. Now the other side over here, my derivative is very positive as well, right? The tangent lines are still very positively steep. So the other side looks like this, and then probably does something like this. That's probably what my derivative looks like. So this was the derivative we were given. We might be able to reconstitute something like this. So the thing is, typically if your graph has a vertical asymptote, the derivative also has a vertical asymptote there, and vice versa. Now you might notice I've kind of drawn this one, but it looks like it has like a horizontal asymptote, like the derivative does, and it kind of does. I'm drawing this like we've got maybe something like y equal to -2, which means that the original function, well, it's kind of funky. Like, how do we get a horizontal asymptote of -2 in your derivative? It's a good question. It's really because there's like a slant asymptote here. That's kind of what's happening, really. Like this function, as you go way out, it's starting to look like something like y equals -2x. And the derivative, that's kind of like y equals -2. It's not perfect. Like, it's I don't feel like I've answered your question very well, to be perfectly honest. But I will say the vertical asymptote part's kind of, it's pretty straightforward. You only get vertical asymptotes keep coming, meaning you can't have a function that doesn't have a vertical asymptote and its derivative then does. It's kind of, or I mean, as I said, I'm like, no, I really don't think you can. Like you really can't. Vertical asymptotes, you have to kind of have one to have them. I mean, unless you guys can think of one. I can't think of one. I don't think you can. Like it seems really, I keep saying that, like, I don't think you can want like this, do that. No, I'm pretty sure you gotta have a vertical asymptote to have a vertical asymptote, which I know sounds redundant, but it's true. Let's look at some examples. I think looking at some examples will probably be helpful. So let's look at this one. Oh my gosh, if I can move the paper. Let's look at the function. Sure. Let's look at x squared divided by x minus 1. Yeah, that makes sense. And typically when we look at functions, we're going to graph this, right? So the very kind of broad directions are graph. But really when we say graph, we mean find all the things. So find the intercepts, find the relative extrema, find the inflection points. And along with that, you're also finding the intervals where it's increasing or decreasing, because you kind of have to define the extrema, and the intervals where it's concave up or concave down, because you kind of have to define where you might have an inflection point. So that's what we're going to do. So you can find the intercepts. The intercepts feel kind of like, okay, yes, we know how to do that. X equals 0, f of 0 is 0 over -1, which is 0. X-intercept, set the top equal to 0. Oh, we get x equal to 0. You also might want to mention the asymptotes. If we have a vertical asymptote that's x equal to 1. We do not have a horizontal asymptote. We do have a slant asymptote, which we'll come back around to later. I usually kind of ignore the horizontal / slant asymptotes unless they're really easy, because sometimes you have functions that are kind of strange that have horizontal asymptotes that you can look back and kind of find them later. I'll give you an example of that in just a minute. So let's go ahead and look at the first derivative stuff. To find the first derivative, you can use the quotient rule. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, which is going to be, you do want to simplify these. So definitely when you're finding first derivatives and second derivatives and you're graphing stuff, you need to simplify so that you can find where you have critical values. So we're going to get 2x squared minus 2x minus x squared all over x minus 1 squared, which is x squared minus 2x all over x minus 1 squared, which I do think factoring is worthwhile here. You get x times x minus 2 over x minus 1 squared. Our critical values. What are my critical values? What's one of them? One time? Right, which is going to be x equal to 1. And then what else? Anybody? What makes the top 0 here? Yeah, and 2. 0 and 2. Now, I want to point out x equals 1, although it's important, is kind of not really a critical value because it's not in the domain of the original function. We're still going to include it on all of our number lines. It's important. It's where we have a vertical asymptote, but we can't have a maximum there. We can't have an inflection point there. It's undefined, right? The original function is undefined there. Just be aware. So my number line, I'm going to put all of my critical points, real or pseudo, 0, 1, and 2. And I'm going to figure out what the first derivative is doing. Okay, well, if x is bigger than 2, my first derivative is positive. Between 1 and 2, it's going to be negative. Between 0 and 1, it's going to be negative. Less than 0, negative, negative, positive, it's going to be positive. And then above that, I like to draw in what the function kind of looks like. My first derivative is positive, and the function is increasing, and then negative decreasing, and then decreasing, and then increasing. So just from the first derivative, I already have a vague idea of what the shape of this thing actually is. In fact, I could probably do a decent job of drawing it right now. And I have a vertical asymptote at 1. And I know I have an x-intercept at 0. And let's see, I'm increasing until I get to 0. I'm decreasing afterwards. I'm going to do something like this. And then decrease. And then after 1, I'm decreasing. And then at 2, I should plug in 2 to figure out what the critical point is there. I plug in 2 to the original function. F of 2 is 4 over 2 minus 1, which is 4. Decreasing until I hit the 0.24, and then increasing afterwards. Do I have everything? No. I mean, from looking at this, I can probably guess it's going to be concave down over here and concave up over here, but I should probably find the second derivative to actually verify that. Let's find our second derivative. So let's see. Point of interest, point of advice. I would much rather take the second derivative of this than the second derivative of this. Or I should say, I'd much rather take the derivative of the first derivative using this form, not this form. I'm going to take the derivative of that. It's going to be the bottom times the derivative of the top, which is 2x minus 2, minus the top times the derivative of the bottom, which is 2 times x minus 1 to the first times 1, divided by x minus 1 to the fourth. Which looks pretty gross. We do need to simplify it so we can see what's happening. And I'm going to point out that I can factor out an x minus 1. Yeah, question. No, this is the graph of the function. Yeah, this is my function f of x. Or this is my kind of best guess at my graph so far. Sorry, one sec. That looks right. Bottom to the top minus top times to the bottom. Yeah, good to go. Okay, and so then this is where things start to get messy because there's a lot of pieces still. So I'm going to point out we can factor out an x minus 1 and a 2 from the top. So I can factor out this 2x minus 2 here, and this 2x minus 2 here. So I'm going to have 2x minus 2 times x minus 1 squared minus x squared minus 2x. All over x minus 1 to the 4th. This 2x minus 2 is really a 2 times x minus 1. And one of those x minus 1s cancels with one of those x minus 1s. So we're left with 2. And then we need to simplify this part here. X minus 1 cubed on the bottom. So we're left with, let's see, x squared minus 2x plus 1 minus x squared plus 2x. And wow, this really simplifies. The x squareds cancel, the 2x's cancel, left with a 1 times 2. So we're left with 2 over x minus 1 cubed. Question?
So when you canceled out the denominator, how come you only like got 1 even though there's 2 the x minus 1?
Well, so let me write a little bit more just a second. So when I did this, here's what I did. I brought out this. What I really have here is this. I have 2 times x minus 1 times x minus 1 squared minus x squared minus 2x all over x minus 1 to the 4th. The thing is, I can't cancel 2 of those with 2 of those because this isn't a factor on its own. It's this minus that, right? So we're stuck with it. Whereas this x minus 1 here is totally multiplying everything else, and that can definitely cancel with one of those. Here's a tip. Whenever you're taking a derivative of a quotient and the denominator is already to some power, so here, like we were taking the derivative of something and the denominator is x minus 2 squared. When you take the derivative of something using the quotient rule, the power of the denominator always increases by 1 after you simplify it. So I know that when I do the derivative of this, I'm going to square the denominator and get some x minus 1 to the 4th. But I also know from experience that I'm going to be able to factor out an x minus 1 and get one of those to cancel and x minus 1 cubed in the bottom. I will also tell you all, if we took the derivative of this and you simplified it, you'd eventually have x minus 1 to the 4th in the denominator. I know when we first do it, you get something over x minus 1 to the 6th because you square the denominator. But then after simplification, you really do get just 1 power higher than you had before. It's not a huge deal, but it is something I've noticed over the years. Oh yeah, every time you differentiate a quotient, after you simplified, the denominator's power just gets 1 larger. So if we want to talk about second derivative stuff here, the only critical point is x equal to 1. So that's the only place where the second derivative is either undefined or equal to 0. Now we know it's not an inflection point because we have a vertical asymptote there. But it's still a place where the concavity does change, right? If you pick something larger than 1, this expression is definitely positive. Pick something less than 1, this expression is definitely negative. Which means our function is concave down over here, concave up over here. But we don't have an inflection point because the function is undefined at 1. And then, I'm sorry. I don't know if anyone cares about you graphing a slant asymptote. This function does have a slant asymptote. Here's how you find it. Slant asymptote, you find by doing polynomial division. You're going to get a slant asymptote exactly when the degree on top is 1 larger than the degree on the bottom. So we're going to do x minus 1 divided into x squared. X times x gives you x squared. X times negative 1 gives you negative x. You subtract that minus that 0, and a 0x minus minus x is an x. And then x times 1 gives you an x. So your slant asymptote here would be y equal to x plus 1. Which, so my graph does not seem to indicate that, right? Like I definitely graphed this not perfectly. So I would go back and say like, okay, well, let's make the graph actually not suck. So here's my vertical asymptote at 1. My slant asymptote is x plus 1, so I need to go through the y-intercept of 1, the x-intercept of -1. And now there's my intercept, and here's the point 2, comma 4. It's going to look like this. So there's a better drawing of our graph. But the point I was trying to make before is once you know the first derivative sign chart. Sorry, I know there's like I'm trying to show you all the things at once. I apologize. Once you know the first derivative sign chart, you know the basic shape of the graph. It's kind of nice. Okay. All right, let's see. I have another example I really want to make sure. Oh yeah, let's do that. So let's look at another graph. Let's say we want to graph f of x equal to, oh, not this one. Let's do this. Let's do this one. It's not quite as terrible. X times e to the x. Again, all the things. So let's find the intercepts. Y-intercept, x is 0. Y is going to be 0. X-intercept, if we set this equal to 0, how many x-intercepts do we get? Well, we set each factor equal to 0. We definitely get x equal to 0. What about e to the x equal to 0? Have any solutions? No, it doesn't, right? Because the graph of e to the x is always above the x-axis. Or you can take the natural log of both sides, and you can take the natural log of 0. So we only got 1 point so far. It's not a lot, but we'll work with it. Vertical asymptotes, there certainly aren't any. Horizontal asymptotes, this is where I would say wait. The way you actually find horizontal asymptotes is by taking the limits to either infinity or negative infinity. So you could say, okay, well, the limit as x goes to infinity of x times e to the x. That's definitely not a finite number. You have infinity times even bigger infinity. On the other side, as x goes to negative infinity, then things get interesting. Because that's an infinity times e to the negative infinity is a 0. So this is a negative infinity times 0, which is indeterminate. It can be anything. Sometimes it's 0, sometimes it's infinity, sometimes it's 1. This is where you have to do something with L'Hopital's rule. If you were in, have you guys done L'Hopital? Okay. Sometimes I feel like it's always scattershot with L'Hopital's rule. Sometimes they teach it in 17 days, sometimes they don't. So, but we'll talk about how you can kind of avoid L'Hopital's rule and still find the horizontal asymptote. If you haven't heard about L'Hopital's rule, don't worry about it. Like if it's something your professor isn't doing, don't sweat it for now. Talk about it later. Or someone else will talk about it later with you next quarter. So let's find the first derivative stuff. When I say first derivative stuff, I mean where the function's increasing or decreasing, which I'm not actually going to write down, and where we have relative extrema, which is all summed up in the sign chart. So I'm going to find my first derivative. I can use the product rule. It's going to be 1 times e to the x plus x times the derivative of e to the x, which also happens to be e to the x. And I'm going to set that equal to 0 to find the critical values. I'm also going to consider where it's undefined, but I know it's never undefined. So I don't have any of the 3 ways something's undefined. Let's factor out an e to the x. So my critical value is x equals to -1. So on my sign chart here, there's a -1. And if I look at the first derivative, I can see that over here, if I pick something larger than -1, like 0, e to the 0 is positive, and 1 plus 0 is positive, positive is positive is positive. On the other side, if I pick something like -2, 1 plus -2 is negative, and e to the -2 is positive or negative. Think about the graph of e to the x for a second. E to the -2 is positive. E to the anything is positive. If you think about the graph of e to the x, it's always above the x-axis, which is why when I said, can e to the x ever equal 0, we're like, oh, no, it can't be because it never touches the x-axis. It's always above it. So what I think when I'm looking at something like this, I'm always like, oh, this part here, I don't even look at that because I know it's always positive. If I plug in -2, oh, 1 minus 2 is negative, it's a negative over here. So my function is decreasing, then increasing. Which means we have a what? A minimum or a maximum? We have a relative minimum at x equal to -1. I'm going to graph this thing, so I also want to find the y value. The y value is, I'm just going to plug in -1 and get -1 times e to the -1, which is -1 over e. I will mention this function also has an absolute maximum at -1 because the function is always right, it's decreasing to the left of it, so it's getting smaller, 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 and then it's increasing to the right of it, so it's getting bigger and bigger and bigger. So that has to be an absolute minimum because there's no other part that's smaller. And this is generally true. If you have one critical point on a function that's defined everywhere, if it's a maximum, it's an absolute maximum. If it's a minimum, it's an absolute minimum. There's no other point that can play that role. Let's look at the second derivative. Something I'm going to say again, just like last time, I typically prefer the unfactored form to take the derivative of. So I could take the derivative of e to the x times 1 plus x. I'd rather take the derivative of e to the x plus x e to the x. I just find that to be easier. So my derivative is, my first derivative is e to the x plus x e to the x. And my second derivative is going to be derivative e to the x is e to the x. And then I'm going to use the product rule again. I'm going to get 1 times e to the x plus x times e to the x. So my second derivative is e to the x plus e to the x, which is 2e to the x plus x e to the x. And I'm going to factor out e to the x. So here my critical value is x equal to -2. We might have an inflection point there. We might not. So pick something larger than -2, like 0, and plug it in, and you get positive times a positive. Pick something less than -2, like -3, negative times always positive. So we are concave down over here, we're concave up over here. So we do have an inflection point at x equal to -2. I generally don't think about finding the y value of the inflection point until maybe after I've graphed it, or maybe not at all, depending on how gross it is. Let's graph the thing. So here's what I've got. I've got my intercept at 0, 0. I have a relative minimum at -1, comma, -1 over e. So -1. And -1, so 1 over e comes up often enough that I've looked at it so many times. I know it's about 0.3. So 1 over e is about 0.3. So I've got about -0.3. So, right, maybe like down there-ish. There's my minimum. So I know to the left, the function is decreasing. To the right, the function is increasing. So here's to the right. It just keeps going up like that. But to the left, I have less choices. To the left, I can't just cross the x-axis because I don't have any x-intercepts. And also I have this inflection point over at -2 where I stop being concave up and start being concave down. Oops, not the best I've drawn this ever. It kind of looks like that. It's so if you're thinking about, I feel like I'm Yeah. And if you've got this thing here, my car is turning one way and then it starts turning the other way. Or, right, your derivative is slowly getting slightly more negative. Right? It's very, very shallow, slightly more negative, slightly more negative, slightly more negative. And then right here, the derivative is as negative as it can be and starts being less negative, 0, positive, positive, positive. So over here, the derivative is decreasing. And over here, the derivative is increasing, which means it's concave up, concave down. And we have to have a horizontal asymptote to the left. There's no other choice. The horizontal asymptote has to be y equals 0 because coming from the left, you're decreasing, but you can't ever be above the x-axis because you can't cross the x-axis. And this happens a lot when you're going in one direction and you are either increasing or decreasing, but you can't cross an axis, but you have to be getting closer and closer to it because that's kind of the only option you have. That's often how you find horizontal asymptotes. Yeah. Oh, I know what it's going to be. Kate. So Kate asked about what about the second derivative test. So the second derivative test is for relative extrema, meaning instead of doing what we did here, so this here, although I didn't say the word, this is the first derivative test. We found a critical value. We looked at the sign chart. We saw that the function was decreasing to the left, increasing to the right. It's a relative minimum. But you can do this other thing, which is not always going to work, which is why I don't like it. But I should point out, it's definitely going to come back up in 17C when we talk about functions of two variables. We're going to talk about how, oh, if the function's concave up, it means you have a minimum. If the function's concave down, it means you have a maximum. And that's exactly what the second derivative test. So here it is real quickly. If C is a critical value of your first derivative, meaning f prime of C is 0 or undefined, then instead of doing the first derivative test, you can say, well, if the second derivative evaluated at C is positive, what does that mean? Well, we have a point that could be a max or a min, and the second derivative there is concave up. Well, it's a min. If it's a critical point, right? If it's a critical point, either the derivative is 0 there or it's undefined. The derivative is definitely 0 there, and the function is concave up around it. That means it has to be a minimum. It can't be something else. On the other hand, if the second derivative there is negative, then you get a maximum. But here's the bummer. If the second derivative there is 0, you don't know. It could be a max, it could be a min, it could be neither. Let me leave you with two examples that I won't tell you, but here are two examples of this. F of x equal to x to the fourth looks vaguely like this. It definitely has a minimum at 0, 0. But the second derivative at 0 is definitely also 0, because the second derivative is 12x squared. On the other hand, this function does not have a minimum at 0 or a maximum. It has an inflection point there. No extrema at 0, 0, but this one still has a second derivative at 0 that's equal to 0. So if your second derivative at a critical point is equal to 0, it's inconclusive. You might have a minimum, you might have an inflection point, you might have a maximum, you don't know. This is why I don't like the second derivative test generally, especially for functions of one variable. If you're looking for relative extrema, maxes or mins, it's always in your best interest to use the first derivative test. But this idea is going to come back to 2 quarters later. We're going to talk about, oh yeah, we've got this function. at this point on this surface, and it's concave down this way, that means it's got to be a maximum. So this idea will come back later.